Hello, this is Jeffrey Fox here again. I'm the instructor for the Big Data Open Source Software and Projects course. This is Unit 12, and we're going to discuss the Big Data application structure using some insights from a recent study by NIST, the National Institute of Standards and Technology. This is the first part of this unit. There are 4 in total. So first, we'll just actually discuss this NIST study. This was an impressive activity. It was led by 3 talented people: Shaitan Baru from San Diego Supercomputer Center, Bob Marcus from Industry T-Strategies, and Wo Chang from NIST itself. He was the overall coordinator, and Baru and Marcus were the clear leaders of the project. So this describes the structure of this project. Notice called the NIST Big Data Public Working Group. There's some important URLs here. The first one, usecases.php, gives you the 51 use cases we'll discuss parts of in this lecture series. And the second one gives the overall report of the working groups, which includes a report from the requirements group, which is, as it says here, is the one that I was involved in, and the main activity of that requirements group was to gather use cases, and we collected 51 in all. There were another 4 important working groups: definitions and taxonomies, reference architecture. That was possibly the hardest one to do because it's quite controversial and not so easy to define. Security and privacy was brilliantly done. That's we will mention its work a little bit. And then the technology roadmap was looking to the future. It had the difficulty that it had to look to the future without defining the present, which is what the other 4 working groups were doing. So altogether, it was a very impressive study, producing important results in all these areas. So first, we'll discuss actually some amusing or interesting results from the taxonomy and definitions working group. And in particular, 2 things they studied was the definition of big data and the definition of data science. And interestingly, data science, which we'll discuss on the next slide, actually was somewhat easier to define than big data, because big data is not quite clear what big means, how big is big, and also what is big describing. Usually big is associated with these so-called several V's: volume, velocity, variety, although there are other V's like veracity, which are also come into play. You can probably define big data, in my opinion, not actually directly by the data, but most important aspect of the big data is how it's used. And it's used to take the data itself to answer important questions. And so that's what it says here. The big data enables novel approaches to important questions. It says here, frontier. These are copied from the NIST report, which are not possible to tackle using conventional methods. Another possibility is that it exceeds the storage capacity or the analysis capacity, the disk or the computing of current or conventional methods. Here we're saying that instead of doing relatively small local samples, it integrates the world's data, population data from all over the world. And another feature of it is we're going to start using parallel computing because it is so large. We're going to need to deploy parallel systems, in particular the famous MapReduce technology and its variants across lots and lots of computers. Horizontally just means that vertically would mean we take one computer and make it more powerful. Horizontally means we take lots of standard computers and spread the problem across them. So the essence of the above is that although you could use size to define big data, That is certainly application dependent, and in fact, it's his usage model which is probably the most important. Here we describe data science. And I was certainly impressed by the number of NIST working group members, the people in this study who actually said they were data scientists. Because until this this particular project, although I was aware of the importance of data science and actually pushing to get it going at Indiana University, I hadn't actually met a lot of people who said they were data scientists. But in this study, there were a lot of people who said they were data scientists. Another important feature, which not just came from this working group, but from other activities I was involved in, I was very impressed by the universal adoption of the Apache Big Data Stack. And that's actually, it was work, and this comes from this time for 2013. That's why this course is actually built around the Apache Big Data Stack. Around this time, I decided it was going to be the future of big data processing. Now, I've been involved in studies as to inventing new fields of study like computational science. And you can ask, what does it take to invent a new field? Well, we know from the first lecture that there are lots of jobs. McKinsey's adding the two types of people together, 1.65 million unsatisfied jobs by 2018. But a job does not define an academic field. So we need to ask whether data science is an academic field. If so, what is its core? What are the key ideas? What is the nature of its curriculum, and so on. You're not going to get agreement on that, but as long as there's a reasonable richness here, you can probably decide that there is a field around here. So one of the best examples of significance of data science is what's called the fourth paradigm, or the data-driven paradigm of science, that was invented by Jim Gray and Tony Hay and others at Microsoft with this online link here. You can find the book on the fourth paradigm. And the essential idea of the fourth paradigm is actually similar to what was stated on the previous slide. Discovery is guided by data, not by a model. And another famous sort of link in this regard is the Ward article, which says that science had reached its end. What it meant is traditional science was changing. It actually isn't even ending. It's being added to by this fourth paradigm. Another good example I use to illustrate the importance of big data is recommender systems, as used by Amazon, Netflix, and so on. And then why I find this recommender systems remarkable is you take pure data, user ratings of movies or products, and they actually use that to predict what users want. So you actually reach a pretty important conclusion of what users like from data. You don't make a model of a user. You just say, we can see in the case of users, you look and see what they want, compare them with other users who have similar likes, and you look at what the other users looked at, and then you say this one user is going to look like these other users and what they like. So this is a pretty interesting idea, because it's not a theory, it's not Newton's law or anything. It's not a law of Mother Nature. It's an entirely empirical law driven entirely by data. This is this End of Science Wired article. And it came actually, this was 2008, when we didn't have as much data as we have today, because it was talking about petabyte, not exabyte or zettabyte. And this article describes this point that the large amounts of data is enhancing this approach to science, which is entirely data-driven, as opposed to being theory-driven. Newton's laws, Einstein's laws, Maxwell's laws. You know, if you go to a physics class, probably even today, you're dominated by laws. Laws are models, and they're not data-driven. They actually came from observation, but those observations are extracted by models. In the case of recommender engines, I doubt if you'll ever make a model of a person. You won't find a set of equations governing people. You will, however, find data allowing you to predict what people are going to do. That's sort of pretty interesting. So here we have the definition of data science. So it's the extraction of knowledge directly from the data through a process of discovery, hypothesis, and analysis. So here we have the components. There's a research component. We have statistics. Statistics is part of the IU data science effort. We have the various domains expertise. If you're an astronomer, you have different expertise from a physicist, which has a different expertise from a Netflix employee. You have various analytic systems. You have algorithms which are used in those analytic systems, and everything lives in a giant pool of Java and Python, etc. And then in the middle, integrating all these things together, we have data science, and all this is bathed in the business expertise. So that's what data science is. And I say this was this multidisciplinary definition is reasonably uncontroversial. There's a rather fancy formal definition here, both of data science and of a data scientist. In practice, it's not so clear that there isn't one data scientist. In fact, McKinsey said there were two types: what we call the decision maker and the technical data scientist. One who builds systems, the other who uses systems. And even there, you're going to have different emphasis. Some will be very knowledgeable about statistics, others on fancy data mining algorithms, and others on use of relational databases and so on. And so so data science is intrinsically is a very broad field that actually makes it good. You don't want to make things too narrow because then you'll define it in a way that it disappears after a few years because the world moves on. But you need data science is the study of these areas. Data scientists need to know a little about all of them. They don't need to know all domains. They just need to know probably one or two domains at least to motivate what they're doing. And the different data scientists will have different degrees of skill in each of these areas. Here we get onto a totally different aspect of the NIST study. I told you this sort of is the hardest. It's the reference architecture. And it defines a set of terms and a set of linkages between these labeled things, which is sort of universal. At the top, we'll have something which you've actually already seen, the orchestration layer. That's the system orchestrator. I told you how that was always needed because you had lots of different components in your system. Here we have various aspects of big data, the analytics. Of course, that's sort of one of my favorites. We mentioned visualization before. We actually studied data access. Curation is making certain that you look after the data and make certain it's labeled properly. Collection is adding all the data together. So these are the various, 5 parts of the data, of raw big data work. And then we have the Hadoop base framework, the analytic tools, the Mahout library, and we have the platform as a service, the infrastructure, the large clusters, and then all lives on a giant sea of computers and networks, software-defined networks, and so on. We have here these cross-cutting things like security and privacy, which remember was cross-cutting in the Apache Big Data Stack. And right at the top is where the value is, because that's where the user or the decision maker is sitting, looking at the results using the visualization tab to see what all of this means. And there is some argument about how wonderful this is. By the way, I forgot to point out the provider of data and the consumer of data here. There is some debate as to how general it is, but this roughly describes all the applications we will look at. And the only wrinkles will be some of the arrows may not be quite correct, but the general components are certainly, I think, very, very reasonable. Here we have a result of the security and privacy working group. They actually came up with some challenges. They also came up with some use cases, which we'll mention later on. But they certainly came up with some challenges, which was sort of interesting where they lie. There's data privacy, many areas such as health and student education and things have incredibly important privacy issues. The infrastructure has to be secure. The data has to be managed in a secure fashion. And you have to worry about the actual real-time activities, the monitoring everything in real time, looking at the various endpoints and seeing that those are safe and not corrupted. And so here are a total of 10 challenges that they identified as critical things to be addressed. We will not really discuss this. This is A, not my expertise, and B, it is, again, it's cross-cutting. I told you security and privacy is very important. It runs in all applications. But typically it is cross-cutting. Namely, the issues you need to worry about to build the system are sort of tend to be decoupled from security and privacy. Now we'll come to what I did. The working group I led was studying requirements, and in particular the big data use cases which drove the requirements. We won't go too much into the requirements. We will study the use cases and their features. And here in this lesson, there are a couple of slides describing that. The first is an easy to understand slide. It's the use case template, where we asked the people who did big data to fill in a template for each of their applications. And we had 51 of these templates filled in. You can see where they are spread. There were 4 in government operations like the Census Bureau, 8 commercially like Search and Netflix, 3 for defense, which we'll actually mention later on, 10 in the important area of healthcare and life sciences, 6 in the nifty area, which I like, deep learning and social media, 4 describing the overall ecosystem and cross-cutting issues for research, like metadata study and things like that, 5 in the application area of physics and astronomy, 10 in the broad area of the Earth, environmental and polar science, and 1 we actually really should have had more in this area of energy. Energy has certainly got lots of important big data use cases, which we did not cover. And for every one of those, we studied these 26 entities. We start off at the top with some rather general issues, the broad area, which I described here, the person who filled it in, who was involved in the use case, who gathered the data, who used the data, what the point of the use case was, and then the description technically of the use case. Then we looked at their current solution. What computers did they use? What storage? What networking? What software? Then we looked at the actual characteristics of the big data. This is slightly vague, whether it's today's data or future data. We got both in the answers. Where did the data come from? An accelerator or a bunch of people or what have you? How big was the data? Tens of petabytes per year for the Large Hadron Collider. What was its velocity? Was it done in batch mode or in real time? How much variety was all the data roughly the same, or was the critical feature of the data multiple types of data? Here's another V, which I didn't mention before, variability. To what extent is the data more or less the same as a function of time? Well, here's one I did mention, is the veracity, which is sort of the robustness, the semantics of the data. Is the data very reliable, without errors, or are there lots of errors which need to be worried about? Well, we have visualization in lots of our charts. That's actually how the decision maker decides what to do. A picture is worth 1,000 words, probably more than 1,000 words. Then we have the quality of the data, the actual syntax of the data. As opposed up here, the veracity was describing the semantics of the data, the different types of the data. Did you have key value data or graph data or what have you? And here we have the analytics. What type of analytics did you want? Clustering, collaborative filtering, typical information retrieval algorithms, and so on. Then we have some rather broadly defined entries. What are the specific challenges for this application area? Did mobile phones present particular challenges? Quite a few of the application areas had requirements in the mobile phone area. Then we have this thing we've discussed many times, security and privacy. Here we put down sort of, again, a catch-all. What is the key feature of this application which is generalizable? So we need to worry about it for the reference architecture. And finally, there was a bunch of URLs, and they were asked to add pictures if they had any pictures. So that was the use case. And here is the last slide. It actually has use cases 23 through 28, the number from 1 to 51. And we here have the file name of where it was first documented. They were reordered to be in order of areas, so these file names are not consecutive. And so here we have epidemiology, social contagion modeling, biodiversity, LifeWatch is a European Union study, deep learning, study of large-scale imagery on the web, Truthy is a Twitter project. Here was the size, so here was, here's what I just sampled some of the 26 features. So here we have the 3 V's, the software used in the analytics. So these are 5 of the 26 features, and you can just see what people put in. Software is here, relational database. Up here it was MPI. Here it was specialized simulators. Here it involved GPUs. Here it involved Hadoop. Here also Hadoop. What is the analytics? Anomaly detection, large-scale least squares analysis, statistics, visualization, and so on. Simulations over populations, models of behavior of people. Here we have velocity. Most of these tend to be done in real time and streaming. Remember, we will show that about 3/4 of the applications use cases were streaming. Here is the variety. To what extent are the systems, the different parts of the system similar? Here we, for instance, say sort of the neural net which is being learned in this deep learning application is pretty heterogeneous. The different layers do different things. And here we have, in the case of biodiversity, studying environment and things, there are lots of different databases of different types. So this is the data. This is just a sample of the data you will find in the online link I gave earlier. This particular set of 5 properties for all 51 use cases. And if you go actually to the same document, it has at the back all 26 features for all 51 use cases. So you can find everything. And there are also actually summaries, which we will actually repeat for some of the later on when we go into a little more depth. So that's the end of this part. The next part will start with a study of how you do parallelism in these different use cases. So this is Jeffrey Fox signing out from this lesson and looking forward to seeing you in part B. Thank you very much.